It's actually my pleasure to introduce Professor William, our first speaker for today. He is actually the head of School of Aerospace, Mechanical and Mechatronics Engineering and the Professor of Marine Robotics at the University of Sydney. So Professor Williams, inshallah, he will talk today about the challenges of marine robotics. Okay, Professor Williams, the floor is yours.
Okay, wonderful. I'd like to start by thanking the organizers of today's meeting for inviting me to speak to you this evening for me, and I guess this morning for you. It's a real pleasure to be able to talk about some of the work that I've done over 15 or 20 years of working in the marine robotics space here at the University of Sydney and the Australian Centre for Field Robotics. So I thought I would start by giving a brief introduction to the center I work in and talk about some of the work that we do before delving into some of the real challenges that we've been confronting in establishing quite a comprehensive program of marine robotics. And I'll show some examples of the sorts of applications as well as some of the underlying technologies and science that we've pursued through this program. So as has been said, I'm based at the University of Sydney at the Australian Centre for Field Robotics, and this is a centre that was established over 20 years ago to conduct fundamental and applied research in robotics across a broad range of application domains. We have about 120 staff and students working on robotics problems in aerial, marine, mining, agriculture, and a whole comprehensive suite of programs that we work with. It's one of the largest field robotics and intelligent systems groups in the world, and we've really sustained the level of activity for more than 2 decades now, and really focusing both on scientific advancement, but also industry uptake and translation into industry. And we've had quite a success in seeing spin-offs of the center in areas such as agriculture robotics, marine robotics. I have a number of students who've gone on to found companies, some defense work and others. We've made really fundamental contributions in data fusion, navigation, planning, control, and systems, and I'll talk a bit about some of how these are applied in the marine domain. And we have a substantial annual budget, which is largely sourced from direct industry partnerships. So we work very closely with industry to understand their needs and to see how concepts in robotics and intelligent systems can be applied to solve real-world problems. This is an example of a subset of the partners we've worked with over the years. One of our big partners, Rio Tinto, is in the mining area. We do work in stevedoring, defense, intelligent transportation systems, logistics, and a number of other areas. I won't talk too much about many of these areas. Unmanned aerial vehicle range. But I thought I'd just show a couple of little highlight videos that capture, I think, the sort of work that we do. So in the top right here, we have a 20,000 hectare flight test facility where we can fly multiple unmanned air vehicles doing ground-air coordination, multi-vehicle distributed data fusion, and decentralized control. In the video that's playing on the top left there is actually a demonstration of an autonomous docking maneuver where 2 UAVs have been used to dock with one another. In the top right, we have very comprehensive programs in the area of high precision agriculture, so using robotic systems to do things like weeding, targeted application of pesticides and herbicides, using a lot of developments in machine learning to really help farmers manage their crops. And we've had a couple of spin-offs in this area who are doing very well and working very closely with our growers on the land. The world is very focused also on intelligent transportation systems and the development of autonomous cars and vehicles, and we have quite a comprehensive set of programs working with partners such as Ford, Coda Wireless, and a number of others in exploring on-road autonomy. And we're working with the New South Wales state government, also through a cooperative research center exploring the future of transportation systems. And finally, I'd highlight the Rio Tinto Center for Mine Automation, which is really looking at the mine of the future and helping Rio Tinto to understand how autonomy and machine learning and automatic planning can be used across their value chain, from exploration, modeling of geological formations and the extraction of ore, and also out into transportation from the mines to ports and then onto ships. So there's a huge amount of work, and that's been over a decade of work in the mining automation area. And I could probably talk at length about any of these programs that we're running, but my own personal work is really focused primarily on the marine domain. And I'm going to talk about some of the work that we've done in that area, particularly in the area with a focus on things like the development of platforms and sensing, navigation and mapping, planning and control, data analytics, and some of the applications that we work on. And I think the data analytics piece is becoming increasingly important as the reliability of platforms increases. The volume of data that we're able to collect far outstrips the ability of human annotators and our scientific partners to keep up with the data. So we really need to turn to computers and automated algorithms to help us deal with the volume of data that we're collecting. And we work with a large group of Australian and international collaborators in this area. And one of our largest programs is actually through a federal government funded, an Australian federal government funded program that is providing the infrastructure to support marine sciences. So this is a program called the Integrated Marine Observing System, and it's part of a national collaborative research infrastructure scheme. You can see it's quite a comprehensive investment by the Australian federal government in the infrastructure required to support the sciences more broadly. So we've recently, about 2 years ago, announced an extra nearly $2 billion investment in infrastructure investments. And the NCRIS program enjoys funding on the order of about $20 million a year. And we operate an autonomous underwater vehicle facility associated with this program. But it also funds moorings and satellite tags and an array of ocean gliders. So there's really been a concerted effort by the whole country to come together, or scientists around the country, to describe the infrastructure that's required to understand Australia's marine estate. And I think we've been very fortunate to be tied into this program. Over the past 15 years or so, we've established a long-term monitoring program looking at changes in the marine estate, identifying key ecological features around the country, and using autonomous underwater vehicles to collect seafloor imagery to help inform ecologists on changes in the biological makeup of these reefs and their responses to changes in oceanographic conditions and climate. And Australia has been affected quite strongly by changes in climate, with increasing prevalence of things like tropical cyclones. We've just, in the last week, experienced extensive flooding through New South Wales and the eastern seaboard, and last year Australia was ravaged by bushfires. So we're really impacted by a lot of these changes in climatic conditions, and understanding what's happening in the oceans and its impact on things like coral reefs is important for our community. So you can see we've been to sites around the country on an annual basis, returning to collect data to allow scientists to evaluate how these areas are changing through time. And we've also been plugged into a number of international initiatives using the capabilities that we've got in marine robotics to support studies in ecology, archaeology, and deepwater geoscience. So we get invited to bring our equipment to sites around the world. In Australia, it's been mainly focused on ecology, but we've done work in Japan, looking at deepwater geoscience sites, as well as establishing some reference reefs in the Okinawa reefs. We've done work through the Mediterranean in archaeology and geoscience, and a bit of work in the Americas as well. So, I think we're recognized for the quality of the data products that we produce and our ability to deploy and recover these sorts of vehicles and collect scientifically useful data. Now, I thought I'd focus the talk around those key areas of research that I talked about. And one of the key things that we've been developing or that we have developed and really exploited, is our ability to do navigation and mapping in a very high precision manner. So we take stereo imagery typically with our vehicles. We stitch that data together to create detailed three-dimensional models of the sea floor with texture mapped overlays of the imagery. So this is an example of some bathymetry derived from stereo imagery. It's calculated down to a resolution of 1 millimeter per pixel. and you can see, very fine detail of these rocky reef environments. This particular data is from Tasmania. And what we'd like to do is provide our scientific colleagues with the ability to understand how these areas are changing through time and over a variety of different time periods that are relevant to the ecological processes that they're studying. So we've done work in the northeast of Tasmania trying to understand or help scientists understand the impact of increasing numbers of long-spined urchins in these reef environments. And this is an image. It's about, I think, 7,000 square meters of sea floor. These are big, large boulders that we surveyed during the day. 12 hours later, we came back and conducted the survey. And you can see urchins that come out from the crevices and are sitting up on the rocks, feeding on the algae and preventing the regrowth of kelp forest, which used to dominate this habitat. But as a consequence of warming around the Tasmanian waters, these urchins have reached plague proportions, and now 15 to 20% of the Tasmanian shoreline is barren, which is having a big impact on fisheries, tourism, and a number of other sectors of the economy that are important for Tasmania. And our ability to navigate these robots back to the same bit of the seafloor allows us to then help scientists really get quantitative information of the prevalence of these urchins without necessarily having to get into the water. So you can see here, this is the same patch of sea floor during the day and night. And you can see that the urchins, which are just barely visible during the day and kind of hiding in the crevices, come out at night and feed on these rocks. Over longer time periods, we're also interested in how reefs are changing as a function of changing climate. So this is some example of some work from Western Australia. There was a significant warming event on the West Australian coast in 2010 and 11. And we conducted surveys in 2010 and 11 and subsequently through a number of years to help chart the recovery or changes in these reef environments. And our ability to go back to the same bit of the seafloor allows us to generate these detailed models that we can work with scientists on to understand how these reefs are evolving through time. And I'll show a couple other examples of this. So this is some plate coral, which has bleached extensively between 2010 and 11. When we come back in 2012 and 13, we can see that the plate coral has died away effectively, but that it's being replaced by branching coral. So this is allowing ecologists for the first time to really understand the dynamics of these reef habitats at the single colony level, which is something we haven't been able to do, particularly in deeper waters. And because we're collecting stereo imagery, we not only have imagery, but we also have three-dimensional structural data, which allows us to chart changes in the structural complexity of these reefs, which then has implications for the fauna, the fish, and other marine organisms which live in these environments. We've also done work in another part of Australia, up in the far northeast of Australia, in a place called Lizard Island. This is in the top end of the Great Barrier Reef. This island was impacted by a tropical cyclone in 2014, and we'd actually been scheduled to be on the island on the day the cyclone hit, so we weren't there. They told us not to come, but a week later, some members of my team were able to fly up and establish some reference sites around the island to help ecologists understand how these reefs recover after being hit by a big cyclone. Unfortunately, another cyclone came through in 2015, and then 2016 and 2017, reefs along the Great Barrier Reef were massively impacted by coral bleaching. So not only we use robots to do some of this survey, but as a rapid tool for collecting this sort of data, we've also been using divers. So we put a little pole in the water, we wrap a string around it, we tie that to the diver, and then the diver swims around in a circle. And we can use some structure for motion techniques to recover detailed three-dimensional models. So this is an example of the recovered estimated path of the camera as the diver swims around. And then what this allows us to do then is build these 3D reef records. So this is about 100 square meters of sea floor. We can go back very precisely to this spot in subsequent years. And you can see here, hopefully that's coming through, the detailed three-dimensional structure of these corals. And this is derived from the imagery that's collected by these divers. And I've actually just had a team up there 2 weeks ago conducting further surveys. Now, we've visited these sites from 2014 every 6 months for the first couple of years, and then every year. And what we can do then is match the data that we've collected to see how these reefs are responding. So in 2014, this particular part of the reef was not very affected by the cyclone. So you can see there's quite a lot of healthy looking coral here, the sort of colored stuff. If we go into 2015, we can see a lot of bleaching. So the coral has all gotten sort of white. And then as we move into 2016, effectively this whole reef has just died. And so the ability to match this reef data allows scientists to really understand impacts on the coral. So here's another bit of reef, the same patch in 2015, and in 2016, again, very extensive evidence of bleaching. So all the colors have kind of disappeared. The little algae that lives in the coral has been ejected, and these reefs are effectively dying. Another part of the reef we see has stayed healthy pretty much throughout, and in fact showed evidence of quite strong recovery in 2017. And our latest, well, actually not our latest data now, but in 2019, we were able to collect data showing that we're seeing new recruits, so new coral coming in to grow on these reefs. So this sort of data is allowing scientists to really describe the life cycles in situ of these coral reefs. And I think that's quite a unique characteristic and something we're able to do. On an even longer time scale, so I talked about sort of changes on the annual time frame. Some of our colleagues have also been looking at how the data that we're collecting can inform climate change impact models. So here what they're doing is they're taking data collected by the AUV along the east coast of Australia. They're charting the distribution of different organisms like sponges and other key biological organisms. And then they're using climate prediction models to predict where the ranges may shift of these organisms in the sort of 50-year time frame. So really thinking forward to what the impacts of climate change might be on Australia's sensitive reef habitats. So I think these studies are all really based on our ability to do navigation, get back to the same place, to tell scientists where we're collecting the data. We also like to think about planning and control, and this is done at multiple levels. So here's one of our autonomous underwater vehicles. This is actually during surveys on a first century BC shipwreck in Greece. So you can see we operate quite close to the sea floor. The vehicle is flying approximately 2 meters off the sea floor. We have a comprehensive suite of sonar sensors and cameras, which is collecting the data, but the sonar and navigation instruments allow the vehicle to very precisely cover large extents of the seafloor, avoiding significant structures like rocks and other outcrops. So you can see we do control at a very low level in terms of ensuring that our vehicles don't crash with the seafloor. But we also have to plan at a much larger scale for multi-vehicle deployments. And this was some work that we did in 2018 in Hawaii with a number of colleagues from the Woods Hole Oceanographic Institute, MIT, University of Rhode Island, and University of Michigan. We basically invited all of our friends to bring their equipment to the ship and to deploy multiple autonomous underwater vehicles, drifters, gliders, and surface vessels all simultaneously. And this became a big planning exercise. So along the bottom, you can see a screenshot of the Gantt chart that we were updating on a daily basis to figure out, when certain vehicles were going to be in the water, where they needed to be recovered, how all the support vessels needed to be deployed. And of course, we're still not at a situation where we sort of have one person to many robots. We're many people to a fewer number of robots. So, it takes a huge team to field this sort of equipment. And this series of videos give you a bit of a sense of sort of what was happening on a daily basis on this ship. So we were deploying gliders from small boats, deploying and recovering a number of different AUV systems, imaging floats. We did some testing and development on unmanned surface vessels. And up on the bridge, we had a map-based interface that showed the skipper and all the science party, where all the assets were, and allowed us to really talk about planning and logistics and when and where everything was going to come to the surface. We had some work from a group at MIT who was looking at, they do a lot of work with NASA on logistics and risk-aware planning tools, and they started modeling the sort of deployment scenarios that we were following. And at one point, they basically came and said, "Oh, we're not going to finish in time for dinner." And I said, "No, we'll be all right." And sure enough, we ended up with a robot surfacing somewhere that we had to go and get. And so I think there's a lot to be said for automation of this planning and taking into account flexibility in schedules when we're working with these sort of multi-vehicle teams. We've also been doing a lot of work on probabilistic habitat modeling and planning, where to deploy vehicles to get most effective data. So we've looked at multimodal learning and inference from visual and multi-beam data. This was presented at ICRA last year. So it's a deep learning framework that learns joint relationships between multi-beam and visual data. So learning the relationships between the sonar, which can cover broad areas of the sea floor, and the imagery collected by the AUVs. And these models then allow us to predict where we might want to collect more data to refine the quality of our model. And we can do this in a fully unsupervised way where we use an unsupervised learning technique to identify clusters of imagery. We can the trajectories. We can then learn that relationship between the visual features and the underlying bathymetry to make a prediction of the map. And not only can we predict the map, but we can also think about the uncertainty in that map. And there's a couple of different features of that uncertainty, one of which is basically the entropy, which measures how uncertain we are. But that gets confused if there are areas that really you can't tell apart. So what we really are interested in is model parameter uncertainty. So where is it that the model is not sure that it might be uncertain? And so we've been developing techniques that allow us to then target areas that will improve the map quality, even if the uncertainty overall remains high. And we can show that by using these sorts of techniques, we can more quickly have a model that converges to a certain level of accuracy in the prediction of the seafloor habitat type. So there's a lot of challenges with planning. There's a lot of uncertainty in the real world, weather, bathymetry, currents, vehicle performance, all these things you can model to a certain extent, but you often can't account for everything. And getting the models at a level of abstraction that is informative and still tractable, I think is one of the big challenges with deploying these sorts of algorithms in real world scenarios. As I mentioned earlier, data analytics has been a big part of the work that we've done over many years. We have a huge amount of data, well over 5 million images of the sea floor. Only a fraction of those have ever been annotated by human labelers. And so one of the conditions of the work that we do is that all this data is publicly available, so it's all online. And we've been building tools that allow machine learning algorithms to actually go in, mine this data, start to use the annotations that people are generating to train classifiers to do this automatically. And we've looked at both unsupervised and supervised techniques to allow us to assign labels to different habitat classes. And this is really changing the way that our science community is thinking about the data that we're collecting. One example of this is some work that a current PhD student has been doing, looking at using the AUV imagery to correlate the presence of lobsters with different habitat types. So here he's trained a machine learning algorithm, a CNN, to detect lobsters in the imagery that we collect. We can then project those detections into a map and really show where we have a population density, while also being able to say something about the terrain rugosity and the affiliation of these lobsters with the seafloor. So these are some examples of the sorts of imagery that we're using. So these are classifications of lobsters. This is trained with a relatively small number of images. So some of the recent advances in classification tools has really improved the effectiveness of these sorts of techniques. And we can then, as I said, map the detections into a sort of heat map of where these things are likely to be located, and then draw relationships between the presence of lobster and different sorts of terrain types, which helps scientists understand their affinity for different parts of the seafloor. But we have to be a little bit careful with this because there are some things that look a little bit lobster-like. So the top row here is things that are actually lobsters, and the bottom are actually sponges. So we have to be a little bit careful in how we interpret the data when we're starting to rely on machines to do a lot more of the classification work. So, there are some challenges with data analytics in terms of the consistency of the labels across environments. We have a relatively small amount of labeled data, and these are often unbalanced across classes. So thinking about transfer learning across data sets, multimodal learning are all areas of active research. Now, one of the most significant challenges, and this is something that we talk about in the marine robotics community, is the challenge of ensuring that the number of deployments is equal to the number of recoveries. So we want to make sure that when we throw equipment into the ocean, that we can actually get it back at the end of the day. And there's a lot of work that goes into ensuring that we're deploying and recovering equipment safely, that we can find it if it goes missing. These are on the top left and right here are images from a part of Australia called the Bass Strait, which is between the mainland and Tasmania. On some days, it's absolutely glassy calm, and it's a real pleasure to work in those sorts of environments. On the left is an example of when my team was on a boat trying to get home in a fairly substantial storm. So it can really affect the ability of our team to work safely. And we've had incidences where we've haven't managed the recoveries very well. We've smashed vehicles up against the side of ships. And one of the things I think that we've been resilient in is being able to recover and continue the work. So this was some work in Tasmania where the vehicle got caught up in a lobster pot. There was a real awkward recovery. It smashed up a lot of the fairings around the vehicle. But we found an old bucket. We put everything together. We got unbent some of the bent metal bits. And the following day, we were back in the water collecting data. And then, there was a bit of work back in the lab to get the vehicle recovered. In other instances, we find there are some significant challenges and risks associated with putting AUVs in the water. This is again that work that I talked about at Antikythera in Greece, looking at this 1st century BC shipwreck. And there's a really fascinating story of some of the artifacts that have been located on this wreck. And we were asked to map this site, and you could see amphorae and various other archaeological items within the maps that we built. And here you can see an example of some of the 3D models of the shipwreck. This is a bit of an anchor stock. So this is a bit of lead that would have been at the top of the ship's anchor. And you can see there the archaeologists. This is in about 70 meters of water. So they're using special gases and things for doing the diving. But they were using our maps to plan their dives. Now we returned for a second field season here. We had plans to cover a whole comprehensive area, which we ended up doing. It looks, in fact, like there's 2 wrecks at this site. So the main site of Antikythera in the north here, and there are artifacts evident in the southern part of this reef area, but not really in between. So it suggests there's actually 2 wrecks on this site. But one of the things we can't always trust this data. So we were given in the background here some multi-beam data. This is a cliff edge here, and we'd planned our dive to be well away from that cliff edge. When we deployed the vehicle, it went on its first dive, and here's the cliff edge, and we watched as the vehicle went down to about 70 meters, and then suddenly the seafloor dropped away from it. It went to 60 meters and then dropped down about 10 meters to 70 meters, in a location where we weren't expecting to see a big cliff. Then turned around, came back, and got stuck. And we had an ROV. Once we'd recovered the vehicle, which we did, we were able to see that it had basically dropped off the edge of this cliff. We put the ROV in the water, which we'd only just recently acquired. I was able to drive the ROV down, find the AUV with the ROV's imaging systems. And you can see, if you can notice, there's this line here that's draped over the vehicle. So essentially the vehicle's turned around at the bottom of this cliff, started coming back up the cliff, and it's got caught under fishing line. Yeah. And so then we kind of looked at it. We thought, what can we do? How can we get this vehicle back? This is sort of the real-time video of what we were seeing on the surface. Managed to get in with the gripper, grab the vehicle's antenna, drive the ROV down, close the gripper on the antenna, and then pull it out from underneath the underneath that fishing line, and then let it go. You know, so it meant we had to shift all of the planned dives back away from that cliff edge. We were able to complete all the work as planned, you know, so we're really using robots to rescue robots, I guess, is one of the takeaways from this one. But, you know, there's that lonely day when people do lose their vehicles. Despite all the hard work, preparation, safety briefings, work health and safety, sometimes things just go wrong. And these are all examples of vehicles that have been lost at sea. You know, some of them in Japan, in the UK, there's one, Nereus was lost in New Zealand at about 10 kilometers of water depth. Yeah, and people will never know exactly what happened in these instances. You know, it might be some sort of failure of the vehicle systems, and maybe some design flaw. But you know, you do what you can to ensure that you get your vehicle back. And about 10 years ago, we were doing some work off Southeast Queensland. We'd spent a week working off a place called Morton Island. I had to fly back to Sydney to actually be in a graduation ceremony. And my team were going to do one last day, half day of sort of mopping up a few extra sites. And I was in my robes, sitting in the grand, you know, the big hall, getting ready for this this graduation ceremony. And I got a call, and the guy said, "Oh, the AUV's on the bottom, you know, and we have no fuel, so we can't stay around to wait for it to come up. We have safety systems that drop weights and the like." In the end, after a long story, the vehicle disappeared. They had to go with the ship to refuel. They came back, the vehicle was gone. We couldn't pick it up on the acoustics. We talked to our oceanographer friends who said the vehicle was probably going north. We talked to the Marine Police who said it was probably going south. So we had all this speculation about where the vehicle might be. We actually got planes, we went out, we searched for 3 days, didn't find it. And then about 2 weeks later, I got a call from a reporter on the Sunshine Coast, which is about 100 kilometers north of this site. And they said, "Yeah, we've actually found your AUV. It washed up on the beach." And they recognized, you know, the Sydney University logo. Some lifeguards pulled it out of the water. We were very fortunate to get it back. And within about 2 months, you know, it looks pretty beat up, but within about 2 months, we were back in the water, continuing our work. So, you know, very lucky. We've since added satellite tracking devices onto our vehicles. There's a lot of safety systems that have grown up out of this experience. You know, but, you know, despite all these challenges, there's been some phenomenal successes in marine robotics, in the discovery of hydrothermal spreading centers, in providing a better understanding of life in our oceans, discovery of new life forms, the cost-effective in situ validation of satellite observations, and of course, the exploration of the deepest parts of our ocean, which really is not able to be done comprehensively with manned systems. And of course, it can all be very rewarding and a huge amount of fun. I really enjoy being out in the field, working with a team of very dedicated staff, and it's really fantastic to be part of this community, both my own team, but also the wider community that's working in this area. And I saw Ayung, who's going to give a talk shortly, and I imagine she might have some similar war stories to share of her experiences in this area. So I think, you know, talking about challenges, I think we've managed to do some pretty special things in the area of platforms and sensing and navigation and mapping. I think the planning and control, there's still a lot of interesting research to be conducted. And of course, in that data analytics, in turning the raw information that we collect into information that's useful for science is still a big challenge. And I think one of our keys has really been in the application domain is to be responsive to stakeholder needs, understand the requirements, and really have a razor sharp focus on delivering data and transforming that into an understanding of the changes in the environment. Looking forward, you know, we're thinking about long-range autonomous marine teams. We're thinking about underwater intervention, so getting robots to actually do things and not just taking observations. There's a lot of work around the world, which I think is pretty exciting, thinking about long-range AUVs, so getting beyond the, you know, one ship with many people with one robot, having fleets of robotic systems out collecting data, helping us understand what's happening in our oceans. And this might be a combination of both underwater and surface vessels. And there's some really amazing stuff happening in the commercial space in terms of deploying these sorts of platforms over very, very long ranges and durations, and some really exciting work here, I think. So I think, in conclusion, marine robotics present a novel tool for collecting rich, high-resolution, and georeferenced data sets. Managing that data, transforming it into data products, continues to be a challenge. But we have some really exciting opportunities engaging with our end user community, and lots of exciting challenges lie ahead. I'm always looking for talented PhD and postdoc positions. And of course, not just in marine robotics, we also have lots of opportunities in mining, agriculture, unmanned air vehicles, etc. And I'm happy to take, if people are interested about the work that I've talked about or any aspect of our work, I'm happy to have some follow-up. Of course, I have to acknowledge a huge amount of support from a variety of organizations who've supported that work, as well as a huge number of people who've been involved in this work. It's certainly not me alone. There's a huge number of students, staff, researchers who've really contributed to all this work. So I'd like to acknowledge their contributions, and once again thank the organizers for the invitation to speak to you today.
Thank you, Professor Williams. Actually, this a really enjoyable and informative talk.
I can see Alexander has asked about uncertainties. We model comprehensively the uncertainties. So we model uncertainty in GPS and USBL. We bring that all into the models that are used by the vehicle while it's underway. We also model uncertainty in these models, as I talked about with the multimodal planning. We're actually modeling uncertainty in the estimation of what is present, the classification of what's on the seafloor, and that allows us to then say, actually, we should go and collect more data from a particular area because we're uncertain about what the model tells us in that area. State-of-the-art localization systems. We use onboard the vehicle. We use actually, we're very careful to use compass and inertial systems, but we also combine that with Doppler velocity logs, which measure speed. Acoustic systems, which are deployed from the ship, which gives us range and bearing to the vehicle. All that is, combined with the GPS on the ship. All that is combined on board the vehicle to allow us to understand where we are. Do you use your experience with rescuing robots to help UUV designers come up with better systems? We certainly have made significant changes to our vehicles based on some of our experience, including adding satellite tags, ensuring that we have mechanical fail-safes that drop weights if the vehicle doesn't surface for whatever reason. So I think we could probably do more on that front, and we could probably keep better statistics on when things go wrong. But we certainly have developed some comprehensive checklists in terms of the sorts of things that sometimes get forgotten when we're deploying these vehicles to maximize the chances that we get them back. And last one, real-time optical communication from an underwater vehicle to a surface vessel. It's something we've talked about. We've certainly been working on using surface vessels to tend the AUVs. So having teams working together over the horizon or remotely from the support vessel is certainly something that we've been thinking about and working towards. And a lot of the surface vessel work that we're doing is really focused on that. We haven't used optical modems today. They generally have a limited range of maybe 100 meters or so, and it depends very much on the water quality. We can get a reasonable amount of information over an acoustic link. The bandwidth is relatively limited still, but we can use those acoustic the systems. And then finally, there's a question about control strategies. We use relatively simple control strategies. The vehicles are, it's a very damped environment for the most part. So we use fairly simple control systems on board to control depth, heading, speed over ground, things like that. And the dynamics of the vehicles are quite damped because of the water and the entrained water and things like that. So we don't use anything terribly fancy. We just have things that are quite robust. So I think that was the questions that are there. So as requested, I'm happy to take a few questions offline and to provide a copy of the slides to the organizers.
Thank you very much, Professor Williams, for this Thank you.
Thank you.